Let's first examine the global offset table. The GOT is fundamentally a lookup table residing in an executable's data segment. Its primary purpose is to hold the absolute addresses of global variables and functions that are located in external shared libraries. When a program is compiled with position-independent code, it cannot hardcode these addresses because it doesn't know where the shared library will be loaded in memory at runtime. Instead, the compiler generates code that references entries within the GOT. Initially, when the program is first loaded, the dynamic linker populates the GOT. For global variables, it fills in their absolute addresses immediately. For functions, the initial entries are often placeholders that point back to the dynamic linker itself, setting the stage for lazy binding. Think of the GOT as the program's personal address book for the outside world. Anytime the program needs to access an external symbol, it consults the GOT to find its current location in virtual memory. This indirection is the key that decouples the application code from the specific memory locations of its dependencies, allowing for the flexibility of shared libraries. This indirection is the key that decouples the application code from the specific memory locations of its dependencies, allowing for the flexibility of shared libraries. Now, let's bring the procedure linkage table into the picture. The PLT works in tandem with the GOT, but specifically for resolving function calls. The PLT itself resides in the executable text segment and is comprised of a series of small code stubs or trampolines. When your application code calls an external function, like printf, it doesn't jump directly to the library. Instead, it jumps to the corresponding printf at PLT stub in the procedure linkage table. Here's where the magic of lazy binding happens. The first time this stub is executed, it consults its entry in the GOT. This entry doesn't contain the address of printf yet. It contains an address that pushes an identifier onto the stack and jumps to the dynamic linker's resolution routine. The linker does the heavy lifting. It finds the real address of printf, updates the GOT entry with this correct address, and then jumps to printf. Now, for every subsequent call to printf, the control flow is different and much faster. The code again jumps to the printf at PLT stub. The stub again consults the GOT, but this time the GOT entry holds the true address. The stub then performs an indirect jump straight to the printf function in the shared library, completely bypassing the dynamic linker. This avoids the overhead of resolving every single function at startup, significantly improving application launch times.